Humanoid robotics, autonomous cars, smartphones, TV remote controls, and coffee machines. In fact, any piece of tech that you own likely has a processor chip primarily designed by one company, ARM. Now, with companies like Qualcomm developing ARM-based chips for Windows, and Apple rumored to have worked with ARM on their incredibly powerful M chips, we might be witnessing one of the biggest shakeups in computing history. And with developing tech like robotics, autonomous cars, and advanced AI, the need for high-performance, low-power chips is becoming one of the most significant factors in getting these products to a usable stage. While Nvidia, with its recent $400 trillion valuation, has become the go-to for GPUs in the space, ARM has quietly been dominating CPU development. But how did ARM get here without making any physical product? What does a CPU actually do? And why is ARM a company that you should be paying very close attention to? We visited ARM at their HQ in Cambridge, UK to find out. Almost certainly anyone who's watching this is, within a meter of a product that is using an ARM-based chip. Paul Williamson is the Senior Vice President of Strategic Ventures at ARM. Some of the end products you'll see around you, everything from your sort of Nest smart thermostat or something like that, they'll be based on ARM technology. In automotive, similarly, there's a dynamic where most vehicles today will have a large number of different ARM-based designs within them. And perhaps in the place that we're most known, the smartphone, 99% are based on ARM technology. So almost certainly if you were using a smartphone, you're using an ARM-based design in the chip that is at the heart of that design. Well, today, we are incredibly excited to announce our first chip designed specifically for the Mac. And we call it M1. In 2020, Apple released their M1 chip, moving away from a long-term partnership with Intel to create their own processors. This marked a major step forward in compute power and energy efficiency. Apple, who had always been known as a premium brand but expensive relative to device performance, was now blowing away the competition at the same price point. While ARM were unable to comment on any relationship with Apple, it's widely speculated that they were involved in the chip design in some capacity. Regardless, ARM's unique position and history of developing high-performance, low-power chip designs probably offers the best option for Windows-based computers looking to compete against Apple's new chipset. While Intel and AMD have made big improvements within their x86 architecture that Windows had historically been built on, they still seem to be lagging behind in some areas. However, the initial results from Qualcomm's ARM-based Snapdragon X series of chips is looking impressive, and the fact that Microsoft has focused on making their recent Surface Books operate on ARM indicates that a big shakeup may be coming in the status quo. Processor fundamentally is a computing device that is going to carry out a series of instructions to achieve a particular task. There are multiple types of processor, and processors can be implemented to achieve different goals. The one that is most important, often in a system, is called the central processing unit. That's the one that will usually run an operating system and the applications that you interface with. While a lot of people understand what a CPU does, not a lot know how it does it. To really understand what companies like ARM do, you need to understand some fundamentals. At the most basic level, a CPU is largely a collection of switches. Most people know that computers operate in the binary code of ones and zeros. This code is useful because it can easily be translated into how an electrical circuit operates, either being on or off. In the case of CPUs, this switch operation is handled by a transistor. The most common transistor in a CPU is known as a field effect transistor, or FET. In basic terms, if the transistor detects an incoming electrical signal, it outputs this as a 1. If it doesn't, it gets read as a 0. These electrical signals can be initiated through peripherals like the mouse and keyboard, and primarily work with the hard drive or RAM, random access memory, which holds data to work on top of, as well as to save for later use. The hard drive operates for long-term storage, whereas the RAM handles the memory needed for instant tasks. Mechanical computers serve as a very basic way to understand how signals and switches can be turned into calculations. Around 1623, Wilhelm Schickard invented one of the first mechanical calculators, which he named the calculating clock. This device ran on a series of gears and could perform relatively complex calculations, including working out the square root of a number. At a basic level, the device operates like this. Numbers 0 to 9 were written on a cylinder attached to a cog with the same number of teeth. A panel with a small window is then overlaid so you can only see the relevant number. For each required decimal place, a new cylinder and cog needs to be added. To carry the one over to the next cog and operate in the same direction, an intermediary gear is added, which is then connected to another one-tooth gear. The one-tooth gear is then set up to push the next cog along by one place every time the first cog rotates between 9 and 0. If you want to add 56 to the number 68, first you have to set up the number 68 in the display window. You then add 56 by moving the second cog 5 places and the first cog by 6. The correct resulting number, 124, should now be shown in the windows. Although vastly more complex, CPUs still operate in a similar way at their most basic level. However, instead of 10-digit cogs, transistors can only read out 2 numbers or states, 0 and 1 or on and off. This value is known as a bit. This means that the calculation needs to be carried over after every second number. Therefore, numbers in binary can be read as 0 is equal to 0, 1 is equal to 1, 2 is equal to 1, 0, 3 to 1, 1, 4 to 1, 0, 0, 5 to 1, 0, 1, 6 to 1, 1, 0, etc. Our engineers have come up with effectively the rulebook or the instructions of how to create a processor, a compute element that lives within all of the chips within the devices around us. What we deliver to our customers is actually lines of code that describe how to put together that processor that is then later manufactured by others, typically a company called TSMC or Taiwan Semiconductor Manufacturing Company in Taiwan. That rulebook, that architecture, as we call it, is really important because it ensures that everybody who then uses that processor, whether to develop software or an app or to create something that runs in the cloud, they all know that at the heart of it is a common set of instructions or processes that will be executed by that chip. While companies like Intel manufacture their own chips, ARM does not. Instead, they focus on developing the architecture, engineering, software, and basically the entire CPU infrastructure that other companies like Qualcomm and TSMC use to develop physical chips with. To understand what these chip makers actually do versus ARM, we need to look at an SoC, typically used in smartphones today. This is a visual representation of the Samsung Exynos 2500 SoC. An SoC, or system on a chip, is the main computing components all merged onto one small chip, basically the brain of the device. Typically, this includes the CPU, GPU, NPU for AI, and aspects like modems. There's a huge range of types of processors. I mean, if you take a smartphone, within it you'll also have perhaps a separate subsystem processor that is just looking after counting your steps and looking at inertial measurements and sensors for activity monitoring. You'll also have a display processor, which is making sure that the pixels are arranged and appear beautifully on the screen that is in front of you. You've got a graphics processing unit as well. That's in there drawing the pixels, drawing the vectors and the images that are used from everything to creating the app interface to also something more advanced like a game that you're going to play on your phone. But fundamentally, they're executing instructions to achieve a particular goal, whether that's rendering a pixel on a screen or deciding, what is the next step to take in the program or the app that you want to run that helps solve the task that you're trying to solve. Each of these components has its own tasks and functions to perform, running on their own targeted hardware, as well as commands and assembly language. Connecting them onto one chip allows for greater communication speeds and power efficiency, but this means that multiple companies can have IP running on one chip. It's the job of ARM's partners to bring this together, make it work seamlessly, and actually manufacture the chip. In the case of the Samsung chip, it has a GPU based on AMD's RDNA 3 architecture, while the CPU uses the ARM Cortex-X925 design, among others, running on ARM v9. The ARM Cortex-X925 is effectively what's known as microarchitecture, which covers the actual physical design of the chip, the components needed to build it, as well as how it operates. It is essentially the IP, or the blueprints, that ARM's partners then build upon. The second main component of ARM's business model is the instruction set architecture, or ISA, with ARM v9 being the latest version. The ISA acts as an interface between the hardware and software, specifying what the processor is capable of doing, as well as how it gets done. The ISA defines aspects like the core functionality of the chipset's capabilities. It can be viewed as a programmer's manual because it's the portion of the machine that is visible to the assembly language programmer, the compiler writer, and the application programmer. These are hierarchical layers of language that gradually translate complex, yet more understandable code into more basic code that dictates the physical chip's functions. Companies like Qualcomm, however, with their Snapdragon SoCs, have CPUs based on ARM's ISA, but use their own microarchitecture chip design. This allows them to be compatible with Android and ARM-compliant apps, but gives them the freedom to customize certain aspects of chip design, giving them potential to dial in aspects like greater processing power or more efficient energy use, for example. In the case of phones, manufacturers wanted as much power as possible while retaining long battery life. The ARM architecture was already being used in cell phones by the likes of the Nokia 3310, so ARM became the logical choice to develop chips for the smartphone era. ARM was originally founded here in Cambridge, in a turkey barn not far from here, by 12 original founders who came together to build a low-power processor as a spin-out from a company in Cambridge called Acorn Computers. The ARM CPU, which was first developed over 30 years ago now, was fundamentally different. It was built with a real focus on power optimization, actually through necessity. The company that was building that processor needed to fit into a power envelope to make sure they could use low-cost technology to package the chip that would fit within the thermals of the device, because a chip that uses a lot of power produces a lot of heat. So they created this architecture that was incredibly power efficient, this RISC or reduced instruction set architecture. Perhaps the first product that it went to be visible and used in was the Apple Newton. The Apple Newton was a sort of Palm Pilot type device with a pen interface, a predecessor to the modern smartphone in many ways. But to be portable and to do the handwriting recognition that was desired by Apple at the time, they needed a performant processor that would fit in that power-efficient envelope. Now, the Newton itself didn't go on to be a huge success, and that meant that ARM needed other customers for that technology that it had developed. And so ARM developed a really innovative licensing business model, which allowed it to share that processor design with other companies who would use it in a range of different products. And it's from that seed of that licensing business model around this core processor technology that the growth of ARM began. Phones were developed around new and unique operating systems like Android and iOS, so not grandfathered into older, less efficient systems like Intel's x86. Because of this, they could be built from the ground up for efficiency rather than just sheer power. The following step that really drove that growth to the next level and pushed the performance demands of these compute chips using ARM technology was the emergence of the smartphone around 2008. And there we saw a real step change in the demand of compute performance, and ARM had to up its game again and deliver a new generation of compute that could meet the demands of multiple applications running simultaneously in a rich operating system or complex device, and that drove a further huge growth wave for ARM in the smartphone era. If you create something that power efficient, that valuable, and it gets deployed into all of these emerging and new applications, it also becomes the basis on which people develop software. If we were the basis of the compute for the first mobile phones, we went on to being the basis for the smartphone. When people were writing the operating systems or the apps to run on those devices, they were writing software for ARM. So in a world where there are now 300 billion chips that have shipped since that 30-year period, there are also 20 million software developers in the world who are writing code that is specifically targeting that ARM architecture and the ARM processor that is at the core of all those devices. The intensive competition in the smartphone industry pushed massive innovation in the ARM chipsets used to run them. This, in turn, made them viable for the PC market and the demand of desktop applications. While these types of chips are evidently capable, and in many ways superior to the traditional x86-based CPUs, we are only now really seeing a big push into ARM-based PCs and laptops. The main reason here is that switching chip architecture requires a complete rewrite of not just the operating system, but the applications too. Apple switched to its M chips, notably involved including a piece of translation software, Rosetta, to enable the use of x86 apps until developers had a chance to update. While this is a good intermediary option, performance of these programs is limited. While personal computers and phones are good public demonstrations, they are just one small part of the upcoming tech that utilizes ARM chips. One of the most prominent ones is robotics. While robotics is heavily connected to AI and machine learning, very little thought is put into the numerous processors and computers that drive the actions of the robot and how they interface with numerous sensors. We now have backflipping, BMXing, kung fu performing humanoid robots, but it wasn't too long ago that these machines were incredibly slow and could barely walk without constantly falling over. As highlighted in the DARPA Robotics Challenge held between 2012 and 2015, just over 10 years ago. We're seeing a lot of interest in automation and robotics. A lot of that goes into retail and supply chains and how you get the products that you want to the place that you want at the right time with the right capability. Having robots that can handle devices, automatically pick and place and position your shopping or your groceries, load and store into shelves effectively in warehousing. All of that can massively improve the efficiency of the supply chain and get the products where they need to be just in time at the right time. But that requires a step change in the compute capability of robotics and automation. These systems now have to be able to process the world around them in 3 dimensions with multiple sensors, fuse that data together and understand the context of the physical world so that they're able to pick and place and move and manipulate objects and potentially even collaborate with each other. It's ARM-based computing at the heart of those systems today for the control aspects of that. But increasingly people are using those ARM compute elements, those ARM processors, to process the AI elements of those systems as well, fusing the data from different sensors into a central environment, and then executing AI tasks which use inference to work out how to handle and manipulate new and different experiences that robotic and automated systems are encountering. Robots are already everywhere in manufacturing. However, they are fairly basic and require uniform, predictable, rigid products to work with. The textiles industry, for example, would be ideal for robotics. However, dealing with flexible, unpredictable fabrics is incredibly difficult to automate. Advanced AI is something that would be required here. This is why videos like this one showing figures O2 folding towels is so impressive. Autonomous vehicles and EVs are another area utilizing ARM. With the introduction of EVs comes a more demanding and intelligent requirement for computers to manage processes of cars. We're seeing some other areas of growth like autonomous vehicles and robotics. For these things to operate independently and to have the smarts to be able to behave and interact with the world around them, we're bringing together in the car ever more compute and sensors to be able to sense the world, and that is requiring a whole range of ARM compute devices, everything from running the charging of your electric vehicle to the camera systems and the fusion of that data into a central brain, if you like, and driver assistance control center, which is then helping to steer and manage the vehicle's functions. Those are all compute tasks that need to be power efficient and really high performance, and that again is a wave that is growing based on ARM. The days of gas cars saw essentially a floating ball cock telling you how much fuel was in the tank. EVs need to monitor battery drain, battery health, and things like management of cell discharge for extended life. In addition to this, manufacturers like CATL are developing hybrid battery types, like fast-charging batteries, high-capacity batteries, sodium-ion cells that work better in cold temperatures, etc., which all have to be managed by a computer to deliver a more well-rounded and reliable driving experience. Not to mention the actual PC-like giant touch interface-based screens that now commonly sit in dashboards, providing operational control for the car. When it comes to autonomous driving, small, highly powerful chips that don't draw too much energy are essential for processing the sensor information to accurately drive the vehicle in a safe manner. Finally, one of the main issues ARM is currently trying to solve is AI power consumption. In the race for companies to create AI platforms and services, a huge amount of incredibly power-intensive data centers are being built. Having more power and more data centers means development of these technologies can happen quicker. However, scaling up power generation risks increasing climate change, pollution, and resource use. One of the big challenges of AI is the scale of compute it needs to solve problems. If we look at data centers, the energy and the growth in compute requirement to serve the AI need is colossal. We're talking about growth in energy consumption that potentially is going to dwarf entire countries just to serve those AI workloads. Now, that's where ARM can play a really critical and valuable role. Our heritage and our DNA in low power is going to position us really well to innovate to bring low power AI compute into these applications. It's going to allow us to develop data centers that are more efficient than ever before, but also bring the power of the data center efficiently down to everything from your smartphone to your car to your in-home assistant. If you're asking, what's the best ice cream in Cambridge? You're sending that to the cloud for a massive data center to answer the question. That isn't necessary. You could absolutely answer that question locally with the right database locally and the right compute capability locally. So we've done a lot of work in creating software, low-level kernels and libraries that can execute AI software tasks efficiently on ARM compute. We call that our Clyde libraries, our Clyde AI, but at the same time we're innovating in the future of those processes, adding more and more AI-type instructions or matrix-based compute into those processes to improve their performance on AI tasks. So your next generation smartphone might not just get a 10 or 15% compute improvement, it might get 100% improvement in its ability to run AI-type workloads and tasks. While ARM may have slipped under the radar for many, their presence in the technology space is becoming increasingly significant and one that most should be keeping an eye on. Designing hardware and software to create faster, more performant devices, but also doing it at a lower power draw than previous technologies, is a task that will not only benefit consumers directly, but can benefit the planet itself.